think we can start. So welcome everyone. So this is a special machine learning coffee seminar. So today we have, I didn't ask how should I pronounce your name?
It's Kyunghyun.
Okay, Kyunghyun. So he's
that's good, yes.
multitask learning. Yep. Please go ahead.
All right, thank you. Thanks for the invitation. And then sorry for not contacting you all, at the early on, so that it has to be scheduled in the last minute. And I'm actually surprised at this coffee seminar without coffee, but we'll have to do with some water. I don't think I've ever actually given any talk at Alto since my dissertation defense. That was a long time ago, so like February 2014. So I'm actually more nervous than ever. Okay, but today I'm going to talk about some very, very basic stuff. And I'm going to start asking some question about a question that I think that I should have asked a long time ago. And then I think a lot of us should have asked me a long time ago as well. And then the first part is going to be about multitask learning. So it's a published work already. But if time permits, I'm going to go into a bit of a unpublished work that we're still working on. We thought we were going to make it for this clear, the causal representation learning conference last year. We missed the deadline, so we're working toward the ICML deadline, which is in about 2 weeks. So, but I'm going to just give you some teaser of what we've been doing in terms of multimodal learning. Yes, yes, welcome. Yes. Yeah. Or you can always just interrupt me and ask questions. Yes. So people from the other side of the Zoom, I don't know how that's going to work, but you can always just unmute yourself and ask questions if you want. So let's start with the multitask learning. Oops, okay. So if you think before in order to talk about the multitask learning, we need to think about what supervised learning is. And then supervised learning is really nothing but building a system, let's call it F, that's going to map input to the output Y. And then this F is unknown, so we don't know how to code it ourselves. So what we're going to do is we're going to rely on the algorithm, learning algorithm, or the paradigm of learning. So we collect a lot of data, and then this data set consists of the pairs. And then each and every pair corresponds to the input and the correct output. And what we do is we're trying to train this F to learn this mapping from the data. All good. But then what we've been doing initially was to make sure that we know how to do that. So that was the early era of the statistical learning theory. And then nowadays, more recently, what we have been doing is to make this function F as powerful as possible. That's the reason why we're using all these gigantic neural networks. And as the classifier becomes more and more powerful, the regularization becomes a key to generalization, where the generalization is defined as trying to build a model that's going to classify an unseen example as well as it can. Now, what does regularization do? So regularization limits the representation capacity of this function, the classifier, you can call it regressor, or the neural network, in a useful way, right? Useful as in trying to maximize the generalization capability. Now then, what is multitask learning? So unlike in the conventional supervised learning, now we have two different types of the outputs. Now it doesn't have to be two, it can be, let's say, as many as you want, but without loss of generality, we're going to say we have two tasks. The original Y is going to be called the main task. So that's the task that we are really, really interested in, while the Y prime is an auxiliary task that is some kind of target, but not necessarily the same target as the main task Y. And then what we want is that we want to train this classifier F to solve both problems. So they're trying to predict Y as well as the Y prime simultaneously given an input, so that learning how to solve the auxiliary task works as a regularization for learning how to solve the main task. So essentially what we're saying is that, well, what was the key to regularization is to limiting the representational capacity of the classifier. So then one way we think, we all believe is a good idea, is to ask it to solve more problems than is necessary, so that this classifier needs to spare some of its representation capacity on solving this auxiliary task, so that there is effectively there is a bit of a limitation on what kind of, let's say, representation it can capture in order to solve the main task. Now, obviously, interesting thing is that okay, hold on, let's actually skip it. As soon as we get to this point, thinking about the multitask learning, almost everyone like this suddenly agree that, okay, this is a great idea. We should do the multitask learning. And then, in fact, a lot of the papers that propose to do multitask learning better than before, they all start motivating multitask learning, or whatever they do, using this, essentially the entire content on this slide. And then they said, okay, this is a great idea. Let's do it better. But then the first question actually that came to my mind was that, okay, how does it actually work? If it worked, what is the right way for it to work? And then whenever you're trying to answer this kind of question, you got to think about some of the extreme cases. And then one particular extreme case, so this is not the extreme case, a extreme case, is that multitask learning simply reduces to single task learning, because now we assume that this f function here is extremely powerful. So why wouldn't it be able to partition itself in half? And then the first half is going to solve the main task y, and then the other half is going to solve the auxiliary task y prime. And then because the f is so powerful, this is going to be as if we never actually had auxiliary task to start with. And then this is probably not what we want when we say that we are doing multitask learning and also solve the main task better. So then what we hope is going to happen, or what we anticipate is going to happen, is that this function is going to somehow partition itself into at least 3 partitions. The first partition is where the input is processed to result in a feature that is more easily solvable by the following 2 partitions, one that corresponds to solving the main task, and then the other one that corresponds to solving the auxiliary task. So this sounds like an ideal scenario. And then this is kind of, let's say, the thing that drives everyone to trying to come up with some specialized neural network that is able to solve multitask learning, or the benefit most from multitask learning. So far, if we just forget about the fact that we are doing science, it sounds really nice, right? It's like the very fascinating concept is that we just give the data set that has not only just a main task, but also the auxiliary task. We train this neural network, and this neural network is going to automatically and magically partition itself into 3 parts that corresponds to feature extractor that is going to be able to extract features that are going to be useful for both main and auxiliary tasks, and then the other partitions that actually do solve those tasks directly. But obviously, then the follow-up question is that what drives this better representation from multiple tasks? If it happens, what is the mechanism behind this magical, let's say partition of the network into 3 parts? Then you go back to the Rich Caruana, who is now in Microsoft Research, or who has been at Microsoft Research forever. His, let's say, PhD dissertation from 1998. That dissertation is actually titled Multitask Learning. Like literally, there is a title. So then you start reading about all his papers that eventually resulted in this dissertation. And then if you look at those papers, you still have a really difficult time figuring out why multitask learning should help. So the Rich actually has a nice list of 4 suspicions he has. Not even confirmed causes, but the suspicions. First one, statistical data amplification. Second one, attribute selection. Third, eavesdropping. Fourth, representation bias. Sounds all good. But the interesting thing is that these all 4 of them were actually presented in a kind of, let's say, 1 page in his dissertation. So it's actually easy to read. I read it over and over. I couldn't even tell what each and every one of these actually means. Oh, what is statistical data amplification? Have you heard about that? No, I don't think so. Attribute selection. What are the attributes here? Eavesdropping. What? Okay, it sounds a bit wrong, right? But then you read it multiple times, and then you notice that what is the one kind of core idea that is shared by all these, let's say, four suspicions, is the fact that essentially the size of the data set grows if we're trying to consider multiple tasks together. Now, of course, in this particular case, we're assuming that the data set, each and every point in the data set may only come with the partial annotations, either the main or auxiliary tasks. But unfortunately, it's still quite difficult to formalize and evaluate whether any of these factors actually happens in order for multitask learning to help us build a classifier that's going to solve the main task better by exploiting the availability of this auxiliary task. So with my PhD student, Taro Makino, who's the first author of this paper, we started to think a bit differently. We decided that, okay, what if we go the other way around? Can we actually, instead of trying to see what people have done so far on multitask learning, and then trying to reverse engineer, what was the thing that actually made all those things that people have tried without actually realizing why they were doing that worked for multitask learning? Can we actually come up with a setup where the multitask learning just has to work in some sense? And then if we have that such a setting, can we actually come up with a way to do multitask learning better for, again, in some sense, right? And we spent like so much time, almost a year, to realize that, okay, we can actually do this. Okay, so it turned out that we can do that. I'm going to just walk you through the whole process that we took for about a year to get to this point, one of the answers to this question. And then what happens is that it turned out that machine learning 101, or if you're students at Auto, the machine learning basic principles, which I believe still exist, is no?
Supervised methods.
It's supervised method. Okay, so things have changed, compared to, let's say, 10 or so years ago. Okay, 13 years ago, we had the machine learning basic principles. And then you learn about all these different paradigms of machine supervised learning. I'm going to actually walk through each and every one of those until we actually end up at a point where we can now say that, okay, here's a setting where multitask learning has to work. And then here's a setting under which we know how to do multitask learning in order to benefit from availability of auxiliary tasks. So let's start with the first one. This is what we learn in the first week of any kind of machine learning 101 course, or maybe the second week. It's a discriminative single task learning. So basic supervised learning, we have X and Y. So we're going to use a circle to indicate that those are random variables. And then we use the arrows to encode our knowledge about the conditional dependence. And then what we're saying here is that, okay, so we draw the X, the input from a prior distribution. And then given that, we're going to draw the label from the conditional distribution over Y given X. And in this case, learning corresponds to, let's look at all those data points in the data set and try to maximize the log probability assigned to the correct label from the data given the observation. And then we do that for every single point. And then we try to find this theta that is a set of parameters that define our classifier that maximizes this quantity. And then once training is done, so we found this theta, we're going to use this theta on a new data point X by simply looking for the Y that's going to maximize this log probability assigned by our model theta, or the F. So very straightforward. In fact, in 2012, there was an AlexNet paper, so the deep convolutional neural network, that kind of changed how we think about machine learning a lot. That one, it literally can be described in these two lines, right? So obviously, implementing the deep convolutional neural network without relying on the PyTorch or the CN or whatnot is like nightmare. But still, if you abstract out those implementation details, these two lines are indeed DEI lines, right? But then, if you recall from the second or the third week of the machine learning basic principles or the supervised learning, then there is another paradigm that is a generative single task learning. So instead of going from X to Y, we say that, okay, we're going to draw a Y, the label from the prior distribution, and then given that, we're going to draw the corresponding input. So that's a generative single task learning. Compared to a discriminative single task learning, all we do is we just flip the arrows. And then in this case, we often call it a base classifier or the naive base classifier, depending on what kind of assumptions we make on the conditions. But the learning side kind of, let's say, looks same. Only difference is that we're not going to try to maximize the log probability assigned to Y given X, but we're going to try to maximize the log probability assigned to X given Y, plus trying to learn this prior distribution over P of Y. And then this is actually pretty nice. This is really nice because it gives us a control over the distribution or the marginal distribution over the label, which actually often change between training and testing, but I'm going to get to that soon. Once training is done, we do the same inference. So we're trying to find the Y that's going to maximize this. But what you see here is that, in fact, these two, the discriminative multitask learning, single task learning and the generative single task learning are exactly equivalent. Because if you recall the Bayes rule essentially says that whatever the arrow you have, you can always flip it. That's all fine. So it doesn't really change anything, except for the fact that we have some better control over the target distribution. That is, if we know that the target marginal distribution changes, so distributional shift happens from the training to test time, we can actually use this, let's say, control that we have over the prior distribution to, to make it more robust. Yeah. Yes. Mm-hmm. Yep. So I didn't actually talk about how this, let's say, log P of the X given Y is implemented. Now you can imagine that once you have some conditional distribution that you don't know how to compute or you don't know how to write down, you can always plug in your own network with the appropriate loss function, and then you can find this. So you can imagine that this is going to be a log loss you're going to use on the X given Y. So Y is the input and the X is the output. Usually we say that, okay, this is super difficult. That's the reason why discriminative modeling is good. But you probably have seen all those stable diffusion, ChatGPT. Turned out that this is actually easier than the other way around for sure. But anyway, yes, so we can use a backprop and then you have to tune all those neural net in order to maximize this quantity as a loss function. Okay. Now, so since we're talking about the multitask learning, let's go back to the discriminative version, but then we're going to talk about the discriminative multitask learning. So we now have the X, Y, as well as the Y prime, because we are talking about the multitask learning. There can be many different tasks, but without loss of generality, I always say that, okay, there are two tasks, main and auxiliary tasks, that's fine. And then we start from the X, so we draw a sample of X from the marginal prior distribution over X. And given that, we draw Y and Y prime. Learning is almost same as the discriminative single task learning, except for the fact that now we want our model to assign a as high log probability as possible on the correct target for the auxiliary task as well. Now I'm writing actually theta and theta prime separately here, but you can imagine that some parts of the theta and theta prime are shared, but it turned out that they don't need to be shared. But let's just say that we are sharing it. And I'm going to just make another assumption that in our data set, we always have the annotations for both Y and Y prime. It's not that complicated, even if we have some of them missing, because we can always marginalize that out, or we can also do the EM-like procedure. So that's fine, but let's just avoid that kind of, say, technical details that are not necessary for me to actually talk about the whole setup. Now, interesting thing is, once training is done, in the test time, we actually throw away the auxiliary task classifier. As you can see, this graph encodes the fact that the Y and Y prime are conditionally independent of each other, given X. So once the training is over, if I want to find the Y, there's a main target that's going to maximize the joint probability of this whole thing. What you notice is that the second term is not is just a constant. We can just throw it away. And this is actually precisely what we do in conventional multitask learning. We train a multitask learner that's going to have multiple heads, right? So that's how we call it these days. And then once training is done, we're going to throw away all those heads that are unnecessary or the auxiliary. But the unfortunate thing is that doing so makes it really difficult to see how multitask learning helps. Because at the end of the day, we just throw this away. So why should it actually help? Right? But before we talk about why they should help, we're almost there. Let's talk about the now generative multitask learning. We talked about the generative single task learning. Now, in this particular case, what we have is that starting from the drawing the Y and then generating X, we add the auxiliary task. Now we draw Y and Y prime from the two different prior distributions. And then given Y and Y prime combination, we draw a sample of X from this conditional distribution. Learning is pretty similar, as in we write down the joint distribution over the entire graphical models. And then in this particular case, we observe all three of them. So we simply try to maximize the log joint over the entire data set we have. But then one thing that actually changes, so before in the single task learning, discriminative version, generative version, exactly same. There's absolutely no difference. You literally can test it yourself. Let's say you collect your data, you're going to build a logistic regression classifier, and then you're going to build some kind of naive-based classifier. And then we're going to assume that the data set actually did follow the data generating process well. You get exactly the same thing. If you get something wrong, and you have a bug, you got to fix that, yes. I think that one of the homework actually was like that. But anyway, but in this particular case, now we have a multitask learner. The generative version and the discriminative versions actually start to deviate from each other. In the case of the generative multitask learning, we can't throw away auxiliary tasks even in the test time. We have to consider the combination of Y and Y prime in order to find this Y that's going to maximize log probability. And then this actually makes it different finally. So this auxiliary task comes in even in the test time as well, not only the training time. And then that this actually raises a question, right? Does this mean that we must do multitask learning now? Because the one thing that any of you who has actually listened and the focus on this is that you might say that, well, what if we just marginalize this out, right? Especially if it's just binary, it's very easy to marginalize it out, right? Why are we actually trying to maximize a joint rather than the version where the Y prime has been marginalized out? It turned out that that's an extremely valid point. And thereby, in fact, the generative multitask learning, again, collapses to the discriminative multitask learning as soon as we decided to marginalize out Y prime instead of jointly maximizing Y and Y prime. But there's a reason why I'm sticking to jointly maximizing over y and y prime. So what actually can happen is that if we say that we want to do the joint maximization for now, and then let's introduce one unobserved variable. So before, the entire graph consisted of the observed variables, y, y prime, and x, but now we're going to introduce z that we're going to call as a target causing confounder. I think that that's a very incorrect name to use, but I didn't think about it that much back then. So let's just call it target causing confounder for now. It is confounder between the different targets. So we have multiple targets coming out of the main and the auxiliary task. And then there's a z, the unobserved variable that confounds y and y prime. Now, in this particular case, let's just assume that this is a case and we want to marginalize out z because we never observe it. So we have to marginalize it out. We don't really have much of an option. Then what changes is that the learning seems almost same, but in this joint distribution, the prior distribution over y and y prime does not factorize into the prior distribution over y and y prime anymore. What that means is that now, because of this z, there's a correlation or the dependence between y and y prime, so the main and auxiliary task. And then the same thing in the inference time, now we have to use the joint prior over y and y prime. So what, in other words, we take into account the statistical relationship between y and y prime. And if you think about it, that should have been the thing that we start with, is that what is the auxiliary task that should help? That should have been the question that we should have asked, right? So many of the papers that you read, you tend to read, see some of the statements like this, right? Is that well, in order to solve machine translation really well, we found some of the related problems like the parsing, post tagging and whatnot, and then we train our machine translation system to solve both translation, parsing together so that this model is going to translate better. In fact, that's exactly what I said in my own paper. So I can actually say it. That's complete bullshit, right? I mean, okay. So who said that, okay, those two tasks are related to each other to start with? But at the same time, when I said that, okay, those two are related to each other so that using parsing is going to help translation, what did I mean by related with each other? So we never actually specified that well. So here, what we are saying is that now let's think about a case where the y and y prime, these two tasks, are a priori related to each other by this unobserved target causing confounder. So we're going to now start saying that, okay, what is the setup in which we're going to consider the benefit of the multitask learning? And then in that setup, we have an unknown variable z that is shared between two tasks, main and the auxiliary task. Of course, we can have multiple auxiliary tasks. And then, so the process of the data generation is that we draw sample from this unknown, let's say confounder. And then given that confounder, we're going to draw the sample of y from the main task and the y prime from the auxiliary task distribution. And then given those the combination, we're going to draw sample of the observation from this conditional distribution. And then once we do this, suddenly we can now talk about why multitask learning, where we look at both y and y prime, is beneficial. Oh, yes. Okay.
So why is this then different from generative single task learning? Because you have the confounder, which is causing both of the two variables, but then causing this x. Like, why can't I just go directly from z?
So, going from z to x.
Yeah.
We actually don't have z. We don't know. This is unobserved. We never observe z. Yes.
Okay.
But then, yeah, still, you're right. Actually, in a sense that why don't we just marginalize our y prime, right? So if you have access to p of x, y and y prime, we can always marginalize y prime by just trying out all possible values of y prime, right? So that's the idea. But it turned out that that's not a good idea, especially in this particular setup, because of some of the concepts that we get out of the probabilistic graphical model. Now, do you still have the advanced probabilistic model course? Is Yako still teaching that? No, I guess not. No, okay. But then, yeah, so there's a course, okay. In that course, like the first, let's say a third of the course is all about how to write the Bayesian graphical model, and then use learn how to use the D-separation, which is kind of useless in general, but it turned out that they can be actually extremely useful once in a while. And then today I'm going to show you one amazing way in which D-separation is really useful. Now, let's say this was the actual data generating process, this generative multitask learning with the target causing confounder. And then I have collected all those data. And then now I want to compute the correlation between X and Y. So I want to compute the, extract the distribution over X given Y, because that's usually what we think of in terms of the generative model, or the marginalizing out all the other variables that we don't see or that we don't want to see. We pretend that we don't see them. Now, what happens is that when we trying to model the X given Y, we are actually capturing two different paths via which the statistical dependence arises. The first path is the direct path, where the Y affects X. That's the direct causal path. But then there is a backdoor path that is created by this confounder Z. Because we have this unobserved confounder, if you look at the D-separation between X and Y, it's not only because of this direct link, but also because of this backdoor path that the X and Y are not independent of each other. So we can now use this rule of the D-separation to see that if we marginalize our Y prime, which is in fact identical to saying that in our data set, we have the X, Y, and Y prime triplets all over, but we just drop Y prime. So there's a marginalization in some sense, right? And if you do the usual generative single task learning, this generative single task learner is capturing two different ways by which X was generated from Y. One is a direct path, and then the other one is this backdoor path. And the interesting thing is this direct path is all fine, but this indirect, let's say backdoor path, in fact, does depend on the prior distribution over Z. So we don't know what Z is, but the prior distribution over Z is going to impact what kind of, let's say, the statistical dependence the Y causes X. And this is where the interesting thing happens, that if the distribution over Z, as well as the distribution over Y prime given Z were held fixed between training and test time, we can marginalize it all fine. So if it's all completely IID situation with the identical distribution between training and test time, absolutely no reason to do the multitask learning, except for the fact that we often get larger data set. Because even if I marginalize it out, this whole thing stays same. So why would I even do multitask learning? However, if there is a chance that this distribution over Z, so the relationship between Y and Y prime changes between training and test time, suddenly single task learning ends up being a very non-robust classifier to the distributional shift happening to this unobserved confounder of the target variables. Yeah. Mm-hmm. Right. Mm-hmm. Mm-hmm. Right. Well, so the self-supervised learning or the pre-training, is pre-training useful because it's multitask learning, or is it actually just finding a good parameter configuration so that if you start from there locally, the loss function is better conditioned, for instance, right? So there will be different ways to explain that one, but I'm kind of skipping the part of how we can actually estimate this conditional distribution. And then whatever the good technique there is, we are going to use it. Yes. And pre-training is going to be, of course, one way for us to do that. Yes. So what that means is that, okay, here it turned out this is a setup where the multitask learning is going to be better than single task learning because it's going to give us a more robust classifier to the distributional shift in the relationship between Y and Y prime, the main and auxiliary tasks. If we do the multitask learning, that is that if you look at the both Y and Y prime, instead of marginalizing out or the ignoring Y prime, because we observe Y prime, this backdoor path closes down. So there's no more backdoor path. And then the relationship between Y and X is completely contained in this arrow. And that's the reason why we want to look at Y and Y prime together, and then trying to solve both the training as well as the inference in a joint way. And once we have this kind of multitask learning classifier, and then if I do a joint optimization of the Y and Y prime, that whole procedure results in a classifier that is robust to whatever the change that happens in the relationship between Y and Y prime. And then that's what we mean by, okay, now here's a setup where the multitask learning is guaranteed to help in some sense, and then the some sense is the robustness to the distributional shift. And then what kind of distributional shift? The distributional shift is in the relationship between these multiple tasks that we have. I'm going to tell you the example because it's kind of like, okay, what could that Z be, right? What could Y be, Y prime be, and X be? But we did run some experiments. I'll show you this soon. But before we go into some of the experiments, let's just quickly, sorry, this one is, okay. Let's just quickly talk about what happens in the inference time and then some of the difficulties there. Now, because we need to solve this joint maximization problem, and then this one requires that we need to have a generative model over the X, which tends to be very high dimensional, given Y and Y prime. So by the time we were submitting this paper, or writing this paper, stable diffusion was only, let's say, I don't know, a month old. ChatGPT wasn't still there. So we're saying that generative modeling is so difficult. But nowadays, it looks like it's not really difficult at all. But then, okay, but let's say it's still difficult. Somehow stable diffusion team decided not to actually give us anything. Well, as they have not actually already. And just had to raise $100 million. And then OpenAI is not telling us anything about ChatGPT, which they are not doing it. And in order to raise, I don't know, like this time, $10 billion. So let's say it's still difficult. From our perspective, it's still difficult. Then we should think about, okay, what is the right way to approximate this whole procedure? And then thinking about the why, in this case, multitask learning helps, is because we're capturing the relationship between Y and Y prime. So what we do is that in practice, we're going to keep this log P of Y and Y prime as it is, but we're going to replace log P of X given Y and Y prime with the discriminative version, because this one is so much easier. Well, that's what we think so far. So we have just a usual multitask learning classifier here. But then when we solve this problem, we're going to take into account this relationship between Y and Y prime. Oh, okay. So let me tell you just one horrible thing about this kind of causal representation learning, or the causal inference in general, is that okay, so maybe a right way to think about it is that, okay, I'm going to tell you the horrible truth about the distributional shift research. Most of them are wrong because they never say how they know to which distribution, whatever the distribution they say are shifting, is shifting toward. So I told you that, okay, this is an amazing classifier that is robust to the distribution shift to Z because it actually ignores Z, right? But then in reality, we are not actually worried that much about the causal relationship between Y, Y prime, and X. We are much more worried about the predictive power on the distributional shift. But then you have to, what is this Z? Z is an unobserved variable. We don't observe it. We don't know the distribution over it. We don't know how the distribution is going to shift. So the one thing that people do, and that we have been doing, is that we say that, well, the distribution over any unobserved variables stays same. Then what happens is that this is a horrible idea because we're going to actually ignore Z. We're ignoring this relationship between Y and Y prime. So what we need to do is that we need to say something about, okay, so what is the situation where subtracting out this relationship between Y and Y prime that arose from the existence of Z, whose distribution may have shifted from the training to the test time. Because what it's saying is that, okay, so Z has some distribution. We're going to ignore it completely. That is, the alpha was set to 1. So we're going to ignore this. And then that means that whatever the distribution Z takes during the training or test time, we don't really care. Our classifier doesn't care. But if the Z distribution stays same between these two scenarios, we actually do want to use the relationship between these two, because that's better for prediction. It's worse for causal inference, but better for predictive modeling. So what we do is that we say that, okay, we are going to introduce hyperparameter alpha that's going to tell us how much we should ignore the shift in Z. But then there comes a question, and comes a reason why most of the distributional shift papers are wrong, is that we don't know how much things are going to shift in the test time. It's supposed to be test time. We don't know, right? So we actually write in our paper that it's impossible. And we wrote in the paper initially that it's impossible. The reviewer said that, okay, if it's impossible, it's useless. So we're like, oh, we'll come up with some heuristics. But let's say that, for the sake of, let's say, testing out whether this setup makes sense, I'm going to start by, showing you what happens to the optimal alpha value. Because you can imagine that the optimal alpha value would be 1 if there's a gigantic shift toward the uniform distribution over Z down the road. But I'll get to this soon. So let's just compare it against the discriminative multitask learning. That is a usual thing that people have been doing in terms of the inference. Now, the first term is the same, but the first term is exactly what the discriminative multitask learning do in terms of inference. It just drops away the auxiliary task. But then in this particular case of our approach, we have to take into account the the auxiliary task classifier, and then we take into account the relationship between y and y prime that was estimated during training time. So we consider y and y prime jointly, and then the influence of, let's say, relationship between y and y prime that was extracted from the training time is actually subtracted out from it. And one thing, and then if you compare against a generative multitask learner, it's all same except for the fact that we now don't assume that the y and y prime marginally or a priori are independent of each other. And one really interesting property is that if you put everything into this framework, we actually don't need to use one classifier to do the multitask learning. We can have two separate classifiers trained separately for the main task and the auxiliary task. And then we can now just combine them together in the inference time after estimating this P of y and y prime. There is a relationship between y and y prime. And then we had this argument about, it can be really challenging with the high dimensional y and y prime, but stable diffusion is all fine. We can always say that, yes, look at stable diffusion, and that's it. So now we have this setup we call generative multitask learning with a target causing confounder, where we know why and how multitask learning should be done and benefit or have a benefit over the single task learning or any kind of, let's say, multitask learning. So unfortunate thing is that as I said, distributional shift research is kind of, let's say, a lot of bullshit there because we actually don't know how to simulate it. And then if you just build a real world data set, we don't know what kind of shift actually happened often. We kind of, let's say, think that some kind of shift happened. So in this particular case, because we had a very precise notion of what kind of distributional shift our approach should be reversed to, so we simulated this kind of multitask learning with the simulated distributional shift using two different data sets that actually don't really have any kind of well-defined notion of the distribution shift. We tried the two different data sets that have many different tasks and many different binary labels, attributes of people data set as well as the Taskonomy data set. Here's one example of the Taskonomy. Now, in the attribute of people, it's just a picture of the people. And then there are a lot of, let's say, labels like this. Okay, does the person wear some long sleeve shirts? Does this person wear, let's say, long pants? Does this person wear short pants and all those things? Now, this is a really nice example. So we're going to create all those binary examples. Now here, y and y prime, long sleeves versus, let's say, short sleeve is going to be our main task. Auxiliary task, long pants versus no long pants, so the short pants. Now, what would be a unobserved confounder, target causing confounder here? Can be just weather. So if it was warm, then it's very good. There's a higher chance that the y and y prime are both going to be, let's say, negative. Let's say short. But if the temperature was, let's say, low, then there's a chance that both, let's say, y and y prime are going to be long. So you can, this actually gives you a sense of what kind of things are those the unobserved confounders that give rise to the multiple tasks. And then by knowing that, you can see that, okay, if I look at both of them together, I can make a better prediction if I can exploit this relationship between those two. So that was a part about creating all those, let's say, different multitask learning experiments. But then how do we simulate the distributional shift? Simulating distributional shift was really difficult. So what we do is that instead of actually creating the actual data set that does have a distributional shift, we just use importance sampling. And then this is coming from the advanced probabilistic method course. Yes, all the things that I learned at the Alton, I'm actually using it these days. So we're going to exploit we use importance sampling. Now then the question is, okay, what should be the target distribution? We have a proposal distribution that is the P of y and y prime we got from the actual data. But what should be this target distribution that we use? And then what should be the relationship between these two that we measure as a proxy to the distributional shift? Initially, we thought, well, KL divergence, or because it's a categorical distribution, probably just any distribution that we can compute, we can probably compute it exactly. So it's all fine. Let's say total variation is a categorical distribution that's just a L1 distance between those two distributions. It turned out that's a horrible way to measure the distributional shift in this kind of classification way. Because let's imagine that I have two Bernoulli variables. The first Bernoulli variable's mean is going to be 0.51, and the next one is going to have 0.49. So their distance is really, really small. Now, another case is that I have a one that has a, the probability, the mean probability is mean 0.9, and then the other one has a 0.51. The divergence is really large, much larger than the first one. But if you think about it, in terms of classification, the first one flipped the decision. The second one doesn't flip the decision. So we had to kind of say, use a divergence metric that actually correlates with the actual number of the flips that you would expect in the classes. So that's going to be what we are going to use in order to tell the distributional shift. And then we wanted to test really like, okay, does it really help in terms of this kind of robustness, regardless of how we estimate these conditional distributions? So we try 3 different cases. No parameter sharing is literally like we have 2 classifiers that were trained independently, and then we combine them. Second one is shared trunk network. That's from just one classifier the 2 has. That's a usual thing. And then there's a third one called cross-stitch network that's supposed to be really good for the multitask learning. We don't see any benefit in real life, but that's kind of a thing that a lot of people use. We decided to use that. And then we made sure that for 3 of these, when we train them and then test it outside our framework, they work as well as or better than the single task learners. Because one thing that a lot of, let's say, multitask learning experiments miss out is that they always compare against the previous multitask learning result, and then say that their multitask learner works better. But if you do the hyperparameter tuning and everything really carefully, you can almost always find a single task learner that works as well as the multitask learners. So that's one of the big issue that we have. So first, let's look at the optimal alpha. So we talked about the alpha values. If the distribution shift is big, the alpha value should be close to 1. If there's almost no distribution shift, the optimal alpha should be close to 0. And then the x-axis here is the distributional shift measured by the weighted candle tau. And then y-axis is the optimal alpha, and 2 different data sets, and then 3 curves correspond to 3 different ways to parameterize these conditional distributions. And then what you will see is that regardless of what kind of, let's say, methods we use to train these models, we always see that as the distributional shift increases, the optimal alpha value does converge toward 1. And then if there's almost no distribution shift, having 0 alpha value is the optimal thing to do. And this literally holds for the case where we had the 2 separate classifiers, one for main and then the other for the auxiliary. So then, of course, the question is that does it actually work better under this kind of distribution shift in terms of the tested accuracy, right? Generalization error. And it turned out that indeed this delta, accuracy delta between the multitask learner, our generative multitask learner, versus the baseline that says a well-tuned single task learner, or the multitask learning without our inference framework, we see that the gap grows as the distributional shift gets worse and worse, or it becomes greater. Oh, these 3 curves corresponds to just 3 different ways of training these multitask learners. So literally, they're almost all the same. This, if I recall correctly, I'm sorry, I'm blanking out. Quick, let's see. Yeah. That's the cross-stitched network, actually, this one that is a bit different from the other, yes. But the difference is actually not that large, yes. All right. Oh, so there is the same 2 data sets, attributes of people, Taskonomy. We actually run it a lot. So this is a mean over, and then the variance is actually pretty small, mean over about 100 or 200, let's say, different tasks that we create from each of the data sets. So then, of course, how do we choose alpha? I just showed you the optimal alpha, and then it's impossible to check, do it. So one heuristics that we came up with is that again, we don't know what kind of distribution shift is going to happen in the test time. That's the major assumption. So we can't really use a test set or anything like that. So instead, we choose alpha to be the biggest alpha that is going to decrease biggest alpha with the tolerance on the validation error with set to some, let's say, value. So let's say I'm going to say that, okay, I can actually tolerate the drop of the accuracy, classification accuracy by, let's say, 10%. Then what is the alpha value, the greatest alpha value that I can get within this tolerance, let's say, drop of the 10%. And it turned out that doing that does actually allow us to find alpha value that makes the classifier much more robust generally, without the minimal, let's say, degradation when there is no distributional shift. So we can actually find some alpha value better even if we don't have any access to test examples. Now, of course, if you have some unlabeled test examples, we can't do that, but you can think about what if we had the test labels alone without the actual input, then we can estimate the P of y and y prime based on those test unpaired labels only. And then we can do it better. But of course, again, the assumption is that we don't get access to the test examples. So that was a kind of multitask learning. So we were able to actually write down a very simple way. It's a relatively straightforward thing to write down a setup that can be provably beneficial, and then provably beneficial in that if there is a relationship change between the if the relationship between y and y prime, the task change from the training to test time, this approach is going to be provably beneficial because it actually builds, it results in a classifier that is robust to the particular distributional shift. So now, if somebody asks you, oh, is multitask learning works, or should it work, then you can just say that yes, in a very narrow sense. Yes, there's a very narrow case where it actually really helps. Okay, so that was the multitask learning. Do I have like 10 minutes to go? Okay, okay. Yeah, yes. Uh-huh.
Saying that in the II setup, there is like no way in which multitask can help, or
no, yeah, that's okay. That's a great question. So I'm not saying that the multitask learning cannot help in other setups. So I'm saying that this is a setup where we can say that the multitask learning is going to be always helpful. Now, there are other cases where multitask learning can be helpful, like for instance, Sanjeev Arora and then all those people at Princeton have been showing that, okay, when you do the multitask learning, under a certain, let's say, assumption that the decision boundaries that are optimal for the main and auxiliary tasks have some overlap, then it can be helpful. So we can, there are people that are coming up with different ways to quantify or the different setups under which multitask learning helps. And this is just one of them. Yes. All right. So then I'm going to actually tell you one thing is, okay, so we talked about the multitask learning. What do we need to talk about? Obviously, we need to talk about multimodal learning, right? And then initially I thought it was going to be so trivial. We just flip it and everything should be done. Turned out that that's not true, unfortunately. So we actually did present the abstract of this at the causal machine learning for real world impact workshop last year. So let's, so multimodal learning. So by the way, definition of multimodal learning is horrible. It's not really well defined. That's our kind of, let's say, third paper in this line that we're actually working on at the moment. What is multimodal learning? Is two-dimensional input considered the bimodal learning? I don't think so, but yeah, okay. But let's assume that we know what multimodal learning is. So you can imagine that, well, I'm going to do some kind of classification or the speech recognition based on video and audio together. Then you can imagine that the video is one modality, audio is the other modality. And again, without loss of generality, I'm going to say that we have only two modalities, but in this case, there's no such thing as a main or auxiliary. We're going to use both of them. And the goal is to build a classifier that's going to take as the input x and x prime combination and then predicts the y. And in this particular case, let's forget about this, the box here. And under this graphical model, what we have is that we draw the x from one distribution, we draw y prime from another distribution, and then we're trying to draw y from this conditional distribution. It looks really weird, right? Because how is that this multimodal learning and the x and x prime are completely unrelated to each other? But it's completely fine, because if we found the x and x prime that don't go together, then simply this P of y given x and x prime, this distribution is going to be uniform. So it's going to be very, the unrealistic one. Although that's still, they're not really satisfying. That's why the third paper coming up, we're writing it. We don't have anything yet, but let's say this is what people have been doing, literally. We build a classifier that's going to take as input, let's say a multimodal, two modalities, and then trying to predict the y. Let's make it slightly more interesting by literally flip what we talked about in the multitask learning. So we're going to now introduce what we refer to as the unobserved true object. We're going to change the name, but let's say that is the unobserved true object. And then these two modalities corresponds to two different views of the same objects. And then given that, we're going to try to predict y. Okay, so far so good. Now the nice thing is that once we draw u from this prior distribution, x and x prime are automatically related to each other because we draw from this conditional distribution that is conditioned on u. And then I was like, oh, okay, so we can do the same thing, right? So even if we had two modalities, let's say we decided to ignore one of them, we're going to use only one of the modalities. Then by building this classifier that goes from X to Y, we know that this classifier is going to capture two different things. One is the direct impact, and then the other is the backdoor effect via this U, unobserved confounder there. An interesting thing is that, again, this classifier is not going to be robust to the change or the shift in the distribution over this true object. So I was like, oh, almost done. Yeah, another paper just automatically coming out, right? But then what you notice is that you wait, hold on, but there is a unimodal learning, but here's a multimodal learning. As soon as we observe both modalities, the backdoor path disappears. The backdoor path just closes down. In other words, in fact, multimodal learning turned out to be the right thing to do if you wanted to build a classifier that's going to be robust to shift in these true objects that we don't observe. So the problem solved. So apparently we were doing multimodal learning really, really correctly. But if you have experience training this kind of multimodal classifiers, what you notice is that it almost never works as well as just really training well a unimodal classifier. It really never does that well. Or you also notice is that the best thing you can do with a multimodal learning is to train two classifiers, one classifier that looks at the first modality, second classifier that looks at the second modality, and then average the prediction. So you make an ensemble of the unimodal predictors. That works beautifully. There's no reason to actually build a complicated multimodal learner. You just build two models and then just combine them. It works really well. So why is that? So in practice, we really see that the multimodal learning is not doing as well as just a unimodal learning. So what is the issue there? When as we can see, this is like a super nice thing to do. It turned out that we actually get an issue because we work with a finite amount of data that was sampled by someone else. So it's a weird thing, but you can imagine that if I have an infinite amount of data, okay, let's go back. Infinite amount of samples drawn from this graphical model, obviously I should be able to get all those conditional distributions perfectly, in particular the y given x and x prime. There's no other, let's say, path. However, when we look at only a small number of data points that were drawn from that original, let's say, let's call it multimodal generating graph, it's possible that because of the noise in the U, as well as the noise in the y given x and x prime, those two types of the noise may look correlated under this small number of data points. We can't really tell the difference. We can't really tell whether U and Y are independent of each other given x and x prime if we have a small number of examples. And then that's exactly the difficulty of the independence testing. You're given any two random variables, and then you need to test their independence. It's really, really difficult. You got to have a lot of data points, or you got to make huge amount of assumptions. So when we look at a small number of points, that happens. And then another way in which this kind of relation, this spurious correlation between U and Y happen is a data set selection. So what if the data set that we were given wasn't really independent draws from this original, let's say, graphical model, but there was somebody who are looking at this data generating process each and every example, and then we're going to have a collider that says that, okay, let's select the example or not. So you can think of the crowd workers trying to choose the simpler ones to earn more money. Or let's say, there were some other environment factors that actually dropped a lot of the examples that should have been there, but not. And then that's called the kind of selection bias or the data set bias from the causal inference literature. And then if you have the kind of collider and then if you condition on this selection, then suddenly there is a spurious relationship between U and Y, even if we observe x and x prime, so both of them. And then what happens is that we're going to go into another concept from one of the basic courses, is that if that correlation was extremely strong between U and Y, to the point that the Y is a deterministic function of U, for instance, U and Y collapse onto each other, resulting in not a Bayesian graphical model, but in a Markov random field. And the Markov random field is what we all love, Alex, right? Yes. It's a Boltzmann machine. Yes. But anyway, Markov random field. So we have x and x prime and y, but now they are related to each other in an undirected manner. And in this kind of case, we make just one assumption first, is that, okay, what is the order in which we're going to consider. So let's say we're going to consider up to the pairwise, let's say, potential. So we're going to have a unimodal potential over y, unimodal potential over x, and unimodal potential over x prime. The latter two can be ignored because we don't really care. We want to find y. And then we're going to put a pairwise potential between x prime and y, and then x and y. Now, because there is no connection between x and x prime, we can't really go beyond the pairwise potential in this particular case. And then we write down this, we sum these log potentials, then trying to find the y that's going to maximize this log potential. And then what you notice is that indeed, what we do is that we try to actually have capture the relationship between x and y and x prime and y separately. And then we try to average the prediction coming out of these two, let's say, modalities separately. So what that means is that if there is a very, very strong statistical dependence of y on u that is unobserved, let's say, input causing confounder, it actually ends up being the case that the optimal thing to do is to train these two classifiers separately and then simply average their predictions. So yeah, it turned out that yes. So if you have a small amount of data, multimodal learning is awesome, but if you have a finite number of data points, or there was some kind of data set bias in how the data set was created, then suddenly u and y are strongly related to each other. And then when the relationship is extremely strong, they collapse onto each other, resulting in a Markov random field where the optimal thing to do is to build two separate classifiers and simply average their predictions. And in reality, it works amazingly, by the way. So if you have any multimodal classification problem, the first thing you do, train the two unimodal predictors, check the accuracy of each one of them, and then just add them up, and then check the accuracy. And then trying to train only the third step, you train this kind of complicated multimodal network, you're going to have so much so much difficulty actually matching any one of these three accuracies that you're going to see. So it's heavily encouraged as a baseline. So then how can we tell? Can we tell is the next question, right? So of course, this is like almost like, well, because we are working with a finite amount of data, we're doomed, okay? That's not that great, so we don't want to do that. So we want to test if that is the case. And then it turned out that we can, what we now refer to as inverted conditional variation autoencoder. Now, this one wasn't taught, yes, at the end of the course, but the idea is that we say that x and x prime always exist, so that's why it's conditional. And then we're going to model the distribution over y. But then we say that, okay, there's a latent variable epsilon that we don't observe that's going to help us model y. Now let's think about this. I trained this conditional variation autoencoder, and then I'm going to look at the second term in the variational lower bound. There is a K of divergence between the posterior distribution over this epsilon given x prime and y, and then the prior distribution over epsilon. If this KL divergence was close to 0 or 0, what does that mean? That means that we could model y given x and x prime without having to rely on extra, let's say, unobserved variable that injects the uncertainty in it. So if we assume further that we know what is the true form of the y given x and x prime, and then we just added an epsilon, and then this KL divergence turned out to be 0, it means that we actually never needed this epsilon. And this epsilon is showing up as if the u from the previous picture. And then this in a synthetic data, it actually like beautifully shows up. So let's say it's all just one dimensional, just a simple, let's say, simulation. We draw u, this unobserved variable. Given that, we're going to draw x and x prime, just two different, let's say, slightly nonlinear one of them, and then we're going to just add them up and then say, okay, y, and then we simulate this kind of, let's say, incidental correlation between u and y by introducing this kind of beta as a parameter. So this beta is the strength of the correlation. And then we're going to train this VA. So forget about delta. So I should remove it. If I look at the KL divergence that I just told you about, if there is no impact, then of course it's going to be close to 0. But as the incidental correlation strength grows, the KL divergence is going to go up because the epsilon actually matters in modeling y, even with the x and x prime. And then this gets worse and worse as the number of examples actually shrinks. So really, it's a finite number of samples that really hurts us because with a small number of examples, we cannot do the independence testing perfectly. And then that's exactly the thing that actually hurts us in multimodal learning. And then I was like, about 2 months ago, I was like, oh, okay, this can't be solved. Maybe the scaling maximalists are all correct. Maybe it's all about just collecting more data. That's the only way we can go about. But it turned out that actually that's not true. Instead, you can imagine that because we train, we can follow some of the literature from the Ixin Wang and Dave Bly from 2018 and 2019. So they had a very controversial paper back then on causal inference, where they said that okay, even with the unobserved confounders are there, we can train a variation autoencoder and then adjust for it, which was like the abomination from the statisticians' perspective and econometricians' perspective. But they were correct though, yes, they were correct. Under certain assumptions, we can actually do that. And then here as well, we can do the exactly same thing. What we did after training this variation autoencoder was that we have this Z that is going to be impact X prime and Y. So that Z, the epsilon, works as a confounder. But then because we have already estimated all these quantities, we can try to intervene and then try to adjust for this confounder by using the same variation autoencoder that we have trained. And how we do that is to, again, using the importance sampling. So instead of using the actual posterior distribution, we're going to use, so instead of using the posterior distribution that actually tells us about this relationship, I'm going to use a prior distribution only, so as to make it into this mutilated graph. Now, unfortunate thing is that the prior distribution is too diffuse. So the variance of this estimator is going to be too high. So we use the importance sampling. So we sample from the posterior distribution, and then we adjust it by looking at the ratio between the posterior distribution and the prior distribution. And doing so, this is again a small scale, let's say, the simulation, the larger scale experiments are actually being run as we speak. But then we do see that the doing so is going to get us a more robust classifier with respect to the strength of the incidental correlation between U and Y. So, yep, what is the summary of this part is that the multi-modal learning should work when the input modalities are different views of the underlying true object. However, unfortunately, due to the fact that we always have to work with the finite data points, and then we always work in a high dimensional space. So the curse of dimensionality is so real. It never went away. It's actually a real thing. So we can't really tell the difference between whether there is a relationship between Y and U or not. So and then that actually kills the whole, let's say, benefit of doing multimodal learning when there is a distributional shift in U. But it turned out that we can work with some of the tools from the causality in order to adjust for it ourselves. So that we can detect it using the generative modeling, and then we can adjust it using the causal representation learning. And then this is very much closely related to Wang and Bly 2018, which is a really nice paper to read. So to finally, finish off the talk, there are actually many paradigms in machine learning that are used and work well in practice, but for which we don't really know when and how they should work. It's a weird thing. So it's almost like the steam engine time. They build a steam engine, it works. The trains are running, the steam boats are running, they're floating on the ocean and so on. But it took us some time to figure out, okay, what is the right way to describe the system? So we're actually entering that time, I believe. And then there are many other paradigms I think we should actually look into more carefully by using different perspective, like the continual learning. There are so many continual learning papers and the benchmark data sets, and I'm like, okay, what is being continued? And how much is the different continual learning versus just IID learning? And then the second thing is like the pre-training and fine-tuning. So how does pre-training actually help fine-tuning? There are so many, let's say, ways in which pre-training can help fine-tuning, but I don't think we have a very clear view of, okay, because of this happened, anything like that. And it turned out that the statistical perspective alone is often not enough, so we have to work with a different kind of perspective. So in this particular case, two cases, we relied a bit on the causal perspectives into the data science, and then that turned out to help us look at it from a slightly different angle. But then what other perspectives are there that we can use in order to explain different paradigms in machine learning? It's a big question. And then that actually is really the end of my talk. Thank you very much for listening on Friday. Yes, thank you.
Any questions?
Way too clear, right? Yes. And also it's Friday, so everyone needs to go, enjoy. So yes, I think we can end it here. Yes. Yes.
Is meta learning sort of like multimodal learning in the sense that you have multiple views over the same time?
So the meta learning or multimodal learning and meta learning are going to be a bit rather orthogonal, but I think the meta learning is actually connected to this continual learning and pre-training and fine-tuning in a sense that there are multiple different tasks that are supposed to be related to each other. And then there is some kind of task distribution that connects all those tasks. And then using that information, we're trying to figure out how the next task is going to be solved better. So it's like continual learning, pre-training, and fine-tuning. Now there, I think that one of the things that we need to think about is that is a distributional shift in the task distribution. Because during the training time, we create all those random, let's say, synthetic tasks. And then we hope that there's going to be a good distribution from which we sample the test in the test time as well. But why would that be the case, right? Yes. So if that changes, would the meta learner actually fail? Something like that. Yeah.
So in the case of device pre-training, actually, I thought that it's a little bit more. Usually, actually, we kind of artificially reduce the number of labels we use. So we are effectively kind of using more data. So since when we pre-train on image, that we effectively use more data. Right. So that could explain how it brings a benefit. But do you have, or do you know of any case where without using more data, a self-supervised pre-training is actually beneficial?
Yeah, I don't think that should be the case in my view. So let's say, of course, I think that the most important thing about self-supervised learning, or the modern version of self-supervised learning, in my view, is the data augmentation. So essentially, one thing we want to start with is that we want, or they end up with, is a classifier that's going to be smooth, but smooth over the potential, let's say, changes that we can expect in the test time, right? So the input images are going to be, we want our classifier to be, let's say, invariant to, let's say, some small translation or some rotations, or sometimes in equivariance if it's a semantic segmentation and whatnot. But then often with a fixed number of the data points that we have, we can't really guarantee that our models are going to have that kind of, let's say, smoothness property that we desire them to. So instead, what we do is that we use a lot of data augmentation in order to find the initial point where from that initialization already these models, these functions are already smooth as we want it to. And then all we do is at the fine-tuning time, we just put the label there. It's already smooth along the directions that it should be smooth. And then all we need to do is just put the labels. So in that sense, I think it's fine to use even a smaller number of data points for self-supervised learning, as long as we actually do use the right kind of data augmentation. But coming up with the data augmentation is super difficult. I don't know how people do that.
Alternative would be to actually put all the data augmentation and then just do normal supervised.
Absolutely, absolutely. I think that's actually, I mean that does help, right, to a certain degree. So, a lot of people do the data augmentation during supervised learning. So then but one thing is that seems like this kind of large scale, let's say, self-supervised learning helps. So maybe there is a reason to use all the data points as well. Well, at the end of the day, space is still large. So maybe just adding a data augmentation, which is almost always local, is not enough to make it smooth over the entire, let's say, data manifold, perhaps. Yes.
One thing that I'm wondering about is whether the order of things, the order of tasks that you train on, or because our models nowadays are so big that it takes a number.
Right.
But then we wanted to train in a way that learns recommendations that are useful for other. So if we train on a hard task, usually it could be easier for the model to just remember the respondents instead of learning the.
Yeah. So the question is, if we want to do this kind of multitask learning, or the continual learning, or the pre-training and the fine-tuning, so what is the right order of, let's say, tasks to be presented to the model learner during training? I don't think there is any answer. Everyone has their own answer. Like literally, everyone has their own answer. But what I think is that it shouldn't matter, because I don't think this kind of the debate about the memorization versus generalization is right. Any large, let's say, classifier, powerful classifier, has to memorize examples. It's like, what is the one of the most optimal classifier you can find? It's a KNN, K nearest neighbor classifier. They, by definition, they just memorize everything. But it's more like these classifiers have to memorize all these examples, but no one says that they have to memorize in trivial ways. So they are memorized in a very non-trivial ways. But then some ways are better than the others for the generalization purpose. So in that sense, yep, it's okay for these learners to memorize everything. Let them memorize. But then now how they memorize is an issue. And then does the order actually matter? So order may matter, but it's not going to be because one is helping, one facilitates memorization over the other. I don't think that's going to be the case. Yeah, classifiers all memorize. They have to memorize. Otherwise, they can't solve the problem. I don't think it's possible. Yeah. Okay.
Okay. So thanks.
All right. Thank you.